far learned about digital informational processes seems to imply that many accepted concepts and laws of physics are informational impossibilities. All of these conflicts are resolved if the finite nature assumption is valid. Finite nature, this is Fredkin 1992, encompasses the following assumptions. At some scale, space, time, and state are discrete, like in many models we have seen during these 3 weeks and the presentations today. The number of possible states of every finite volume of space-time is finite. There are no infinities, infinitesimals, or locally generated random variables. The fundamental process of physics must be a simple deterministic digital process. When we say that we have a computer model of some system, we normally mean that a subset of the data in the computer can be mapped onto the system being modeled. We might be able to demonstrate that an ordinary computer model of physics is sufficient, but we cannot normally show that it is necessary. The reason is that any and all models of finite nature can be replaced by equivalent computational models based on any universal computer. This business of many models being universally, universal computer, and therefore, in a sense, equivalent. Digital mechanics, or finite nature, I would say, implies that there is a computer-like model that has a bijective mapping one-to-one from states and function in the real world of physics to states and function in the model. This imposes absolute requirements that the computer-like model be spatially organized like cellular automata, be reversible, and be computational universal. The beauty of this idea of the one-to-one mapping from the formal model to physics, the beauty of this one-to-one mapping restriction is that it delivers us from the apparent tyranny of computation universality. So it's unlikely that there will be more than one such correct model. The idea here is that, put forward by Fredkin, is that there might be only just one model, one formal model of computation in which every single step of the computation corresponds one-to-one to, let's say, potentially visible or measurable piece of physics, phenomenon, variable. So this one-to-one thing probably might solve the problem of having so many alternative, universal, Turing-complete models of computation.